Okay, so homework for today was to do the Fizzbuzz dealy flippy, right? All right, how'd that go? Should have been fairly easy. We've done it before in Python, and now we're just converting it over to Java and running into a couple of little idiosyncrasies you might have with Java, but in general, not too bad. Okay, so let's go ahead and we'll write that. Then we're going to convert that into a function. And then we're going to start talking about strings a little bit. So let's get rid of all this stuff. So last time we spent quite a bit of our time talking about variable scope. Remind me, what is that? When I say variable scope, what am I talking about? Lively, lively crowd. Go ahead. Yeah, where we have access to the variable, and that's driven by where we've defined the variable, right? So we talked last time how the for loop kind of gets its own scope, and how we have a scope related to a method, and we have a scope related to the class. And when we define a variable, we get access to it from that point forward within its scope and any scopes that live within that scope. Okay, so it's I would say in general, you want variables, if you had to throw a rule of thumb on this, you want variables defined in the most local scope that you can get away with. There's a kind of a saying in computer programming, this idea that global variables are bad. All right, so the idea there might be that if you have a whole bunch of variables up at the top of your program for governing every little thing that happens anywhere in the entire application, you're going to have a whole bunch of variables and you're going to start losing track of what's what. You also then lose the ability to have variables with similar names for different contexts. So generally speaking, make a variable as local to what you need as possible. And then if you need to make it a little bit more global, you need to move it up a scope in order to make it available to some additional things, additional areas of your program. Do that, but don't just haphazardly throw everything up at the very top and say all of these are available to everything. Something we're going to eventually talk about in here is something called a singleton. And I maybe even mentioned it last semester. Did anybody remember if I talked about singletons at all last semester?
I heard mentioning it, but didn't really.
Okay. So we could just as a general thing, and this will make more sense later on, a singleton is like a super global variable. Okay, so we have a little bucket that's available to everything in our entire application across multiple classes, multiple objects. So there is a time and place for those, but you certainly don't want to put everything inside of a singleton. Otherwise, you have 300 variables that belong to some aspect of your application strewn all over the place. Another thing I want to announce before I forget. So I put up a post about a hackathon a couple of, I guess, last week. So we have an upcoming hackathon that is not this weekend, but next weekend. It's in Champaign, Illinois. I'm arranging, transportation for us. So we would be leaving Friday night or Friday late afternoon, let's say. Probably 5 o'clock, something like that. Staying in Champaign for the night, going to the hackathon the next morning. Then the hackathon is a computer programming competition that lasts for 24 hours. I think we're going to try to focus on doing some augmented reality stuff with Apple's AR kit. Now that stuff is becoming kind of a, it's going to be very prevalent in the app stores, and Android is kind of jumping on board. They're going to have their own augmented reality stuff. I'll be forming teams based on what will be the best educational experience for you. So you do not have to be a great programmer or have a lot of experience in order to go. Beginners are welcome. We already have several people who are more experienced who have signed up, so they would be team leaders and will help you learn. The goal isn't necessarily to win the hackathon. You get free food at it. It doesn't cost you anything except your time. All right, so effectively it's you would get something along the lines of, let's call it a semester's worth of education in a 24-hour period. You learn quite a bit of stuff. at a hackathon. So I'd strongly encourage you to take advantage of that. But I do need to know as soon as possible if you are able to go with us, so I can make sure we have enough cars for the caravan down to Illinois. It's about a 4-hour drive, so not horrible distance, but it's down there. And if you can pull an all-nighter, that's great. If you require some sleep, that's fine too. I would say at least half the people end up taking naps or whatever, but just a good experience to just see the process of creating a full application when maybe you haven't done that before or haven't been part of that. And everybody will find a way to contribute, even if your physical contribution to it is minimal. You'll learn a lot, and you'll have something to work on that will contribute to the project. So strongly consider that and try to let me know. I mean, if you could let me know today, that would be awesome. But let me know within the next 2 days, let's say, so I can make sure we have enough vehicles as well as accommodations for Friday night. Questions about that? Okay. Out of curiosity, how many of you think you might be interested in doing it? This isn't a commission. You're not committing right now, but you're okay. So you might be interested. Okay. So two and a half people. So again, strongly encourage you to do that. We will have our hackathon here on campus. I think it's going to end up being sometime in November. Professor Josh Locklear is putting that together now. So the more information will come out for that. That's a 12-hour hackathon. So you show up in the morning, we're done, later in the day. But traditional hackathons are 24 hours. So you go and you're sleep deprived and you get cranky and all that stuff. But it's a good experience. And I mean, I think if you talk to some of our seniors who have done these things, you'll get pretty solid feedback. We used to do this one called Battle Hack, which is kind of a professional programming competition, not just for students. And we traveled, we went to Raleigh, North Carolina one time for that. We went to New York City. Chicago was the easy one, so our starting one was we went to Chicago, and then we almost went to Los Angeles. We were looking at doing the Los Angeles one, and we just couldn't pull the funds together to do the travel out there. But in any case, there is think of it like kind of like a sports team thing where you get to do a road trip to go and do something, and typically it either costs you nothing or minimal. Whether you're responsible for your own food or something during the travel, but the department has historically helped quite a bit with the thing. So those are good experiences that I would encourage you to take advantage of when we go and do these things. Okay, so let's solve Fizzbuzz first. We'll solve it just inside main initially, and then we're going to move that into a function to kind of appreciate some of the value in that. So let's see, for Fizzbuzz, we're going to go through all the numbers between 1 and, 1,000? All right, so before we do anything else, we need a loop that goes through all the numbers between 1 and 1,000. All right, so this is going to be our standard for loop. So for int I is equal to 0, I is less than, actually we're going to 1 to 1,000, right? I is equal to 1, I is less than or equal to 1,000, I plus plus. Okay. What's the advantage of defining I inside the for loop there? Scope. Okay, so it lives and dies with the for loop, right? Okay. So when we get to this line right here, I no longer exists, so it's free to use again, or we can redefine it. All right, so just for the sake of argument right now, I'm going to say system.out.println I. Let's just prove to ourselves that we get 1 to 1,000 printed out. All right, so there's 1 to 1,000. All right, now while I'm at it, let me just show you something else here. I'm going to do 1 to, let's see. That's 2 million. It's 2 billion. That's 2 billion, right? All right, so we know that the largest integer we can have is positive, it's like 2.1 billion. All right, so right now this is starting to push the maximum size of an integer. So I'm going to go through this for loop 2 billion times. That's a lot of times, right? So I'm going to go ahead and hit play on this, and you're going to see that this guy takes a while to run. Still cooking, still cooking, still cooking, and what we're not even halfway there yet, right? So now I'm going to define a variable here called int count. Start that guy off at 0. I'll say count plus plus in here, and then I'll go ahead and print out count afterwards. How long do you suspect this program will take to run? Way less time. Why is that?
You're not printing it 2 billion times.
Okay, so printing must be expensive. Do we know why printing's expensive? It's not the CPU's job. So, we think of, generally when we do like the initial hello world program or something like that, we think of, oh, spitting something to the screen, that's not a big deal. Well, spitting something, to the screen once or twice, not a big deal. But we just tried to do something to the screen 2 billion times with very, very little logic in between. So what happens is when the task of adding 1 to a variable goes to the CPU, so our program waits in line for the CPU, gets to the CPU, it adds 1 to the variable, then it says, oh, my next thing is to print something. It has to do what's called a context switch. So he goes and gets in line for I/O, so he leaves the CPU, which is an expensive task. Getting onto the CPU initially, and then leaving the CPU, the way I usually describe it is kind of like checking in and checking out of a hotel. You have to unpack your bags, you have to pack your bags. That's not an instantaneous process. All right, so having said that, if we're just going to come into the CPU and add 1 to I, we're not using our entire allotted time on the CPU. We're unpacking our bags, we're going into the bathroom, checking ourselves in the mirror, packing our bags, and leaving. Okay? Not an efficient use of a hotel room, right? Usually we're staying overnight or something like that. Right? So it's very inefficient on the CPU. Plus, we have to get out of line to go and print something. Then we have to get back in line and wait to check back into the hotel room again in order to add 1. It's a very expensive process. Whereas when we didn't do I/O in here, we didn't print anything inside the loop, we get to add 1 to count, and in this case we're adding 1 to 2 different variables, a whole bunch of times in our single trek through the CPU. All right, so when this guy waited in line to get access to the CPU, he maybe got to add, let's just pick a number, 5 million times. Okay, because adding is a fast thing. Our processors are very capable of doing it. So it didn't take us that many times to get onto the CPU in terms of human perceived time, right? It didn't take us that much time to actually count to 2 billion. And then we just print it out once. That makes sense, the speed difference? Even though our code really hasn't changed. All right, so go ahead.
Is there a way to make it print? Because the CPU have multiple cores.
Well, the issue here is not our CPU. I mean, the issue here is that for anything to print out, it has to leave the CPU and go and work with the I/O subsystem on your computer, on your operating system. So it's not that our CPU doesn't have enough cores. It's that we're not utilizing the horsepower of our CPU when we're on it, when we have access to it. And the CPU's not, as he pointed out, the CPU's not in charge of printing stuff to the screen. So we have to go wait in line for I/O, which doesn't take very long. But then we have to go wait in line for the CPU, and now we're in competition with the other processes running on the computer. Now, with multiple cores, let's say you have a 4-core processor. So now you can do 4 things at once. So that's like waiting in line at McDonald's, and there's 4 registers. So that line's probably going to move more quickly than if there's only 1 register, but you're still waiting in line. That makes sense? So that's kind of the process. All right. So in any case, we are going through all the numbers between 1 and, let's throw 1,000 back up here. All right, so these are the numbers we want to apply our Fizzbuzz Logic to. And Fizzbuzz Logic says what? If a number is evenly divisible by 3 and 5, we print out Fizzbuzz. If a number is evenly divisible by just 3, we print out Fizz. If a number is evenly divisible by just 5, we print out Buzz. Otherwise, we print out the number. Does that sound accurate? Okay. So we're going to ask we're going to go top down. We're going to ask the most exclusive question first. Is the current number we're looking at evenly divisible by both 3 and 5? So if the current value of I, when divided by 3, gives me a remainder of 0, that means evenly divisible, right? So if I mod 3 equals 0, now notice this is the double equal sign. This is the equivalence operator. Is something equal to something else, right? It was the same operator we had in Python. So if I mod 3 is equivalent to 0, and I mod 5 is equivalent to 0, it's evenly divisible by both of those guys, then we want to, what's our response to that? Fizzbuzz, like that. I don't remember if there was a space in there or something, but whatever. Close enough. So now common programming mistakes people make. They'll say something like, if I mod 3 is equal to 0 and mod 5 is equal to 0. They don't think they need to say that I a second time. And now, my question is why do I have to say that I a second time? The correct answer is not that that's just the syntax. Go ahead. Were you offering an answer or not yet? Do you have your hand up?
Oh,
No.
no,
No, okay.
sorry.
No, that's fine. Go ahead.
Because and is like, it's like two different statements. When you put the two and sign, it's like you ended a line. It's like the semicolon.
Okay. So what's this do? This is and, right? This is what we would call the logical and. So let me just kind of flesh that out a little bit, just in case you make a mistake sometime. So this guy right here, I would call this guy the logical and. And the reason I want to point this out is, and did any of you do this? Did any of you accidentally just use 1 ampersand between your Boolean expressions?
One times.
Okay, but it didn't break, right? Well, actually, you still had Booleans on either side, so it would have given you an error.
Yeah.
But for instance, 5 and 3, which when we look at that, we would say that doesn't make any sense, right? That works. 5 and 3 is logical when you use a single and symbol. And the reason for that is this guy is called the bitwise and operator. So when you say 5 and 3, what it's actually doing is it's converting 5 into its binary equivalent. Okay, because that's how it's actually stored under the hood. So this is the ones place, this is the fours place, the twos place, the ones place. So this is the number 5, right? So this is the ones place, this is the twos place, this is the fourth place. So 4 times 1 is 4, plus 1 times 1 is 1. So that's 5. Then a 3 is 0, 1, 1. And then what we're doing is we're anding the individual bits. So 1 and 0 is a 0. A 0 and 1 is a 0. A 1 and 1, both of them are true. That's a 1. Okay, so the answer to 5 and 3 would be the number 1. That's what would print out to the screen. Now, at this point right now, we don't have a use for that, right? We can't come up with an example. This is something we'll deal with like in a computer architecture class. We're doing bitwise actions like this makes sense. But the reason I wanted to point it out to you, we won't use this in here, but I wanted to point it out because this is a mistake you might make. You might use 1 ampersand instead of 2. And if you couple that with not using Boolean expressions on either side, you're going to run into problems. Because we talked about a couple classes ago that in Java, the Boolean primitive type, while under the hood, it is implemented as a byte. Okay, it's implemented as numerics because computers like numbers. Okay, it's good at storing numbers. And again, that'll make sense when you take like 325, which probably is next semester for most of you, right? It's 325 next semester? Computer organization and architecture.
I have,
Yeah.
that makes sense. I have 300 and 370.
Yeah, you're going to be in 300 with me, 370s with Dr. Locklear at software engineering. If 325 is offered next semester, you should be in it because it's only an every 2-year class. I'm not sure. I teach it, but I'm not sure if it's offered. I'll find out. Well, I can check now, but
Yeah.
I'll become aware of it 2 days before classes start.
Yeah.
Is when I will put it into my calendar, and then I'll prep for it week 3.
But they'll send you the email 1 week before class starts. So that's pretty nice.
But they send you the email for that?
No, I'm just assuming that,
No, I don't get an
they
email.
would alert you.
No, I know.
If you're teaching.
No, that's not the way it works.
Oh, wow.
We gotta log into Banner and find out what our schedule looks like. And then they always warn us, like the day before class, that your room numbers may have changed because they have to shuffle all these rooms at the last minute because we have 300 classes and 290 rooms. It becomes very interesting. All right, so in any case, in an older language like C and C++, the Boolean primitive type actually is numeric. You can do math with it, even though that never makes sense. We would never say true plus false and get an answer, right? True being a 1, false being a 0, so 1 plus 0 is 1. Why would I do that? But in those older languages, you could. So one of Java's kind of Emmos, if you're trying to determine what Java likely does for a situation. Because one of the skills you get as a programmer is the ability to read code. And even if you're looking at syntax from a language you haven't necessarily worked with, you probably can read it. We've seen this over the last couple of classes. Most of you have been exposed to Python previously, and now you're starting to see Java syntax. So even if you hadn't seen Java syntax before, it wasn't completely foreign to you, right? You probably could have read it. You probably could have looked through it and say, okay, I get what that's probably doing. Maybe every now and then you'll bump into a symbol that wasn't the same. For instance, double ampersand or something, because in Python, actually in Python 2, it is double ampersand, but in Python 3, it's just the word and. But regardless, we could pretty much read Java. Now we're kind of practicing writing it, getting some muscle memory for some of the weird symbols and that kind of stuff, and the curly brace thing and all that stuff. So one of Java's MOs is that they tend to take things from the languages it's based on, so let's say C++, and things that don't make sense, Java makes it off limits for you. Okay, so the example I've always used is, the Java textbooks typically say that pointers don't exist in Java, when the reality is everything's a pointer in Java, is the punchline. So the example I use is that a language like C++ empowers the programmer to make poor decisions. For instance, if you're inviting somebody to your house, you can hand them the house and tell them to open the door at 8 instead of giving them the address where your house lives. Yeah.
So just talking about stuff that Java does or does not have that's from old languages. The question mark, colon.
Yeah, that's a single line if statement. It does have that.
It does?
Yeah.
Okay.
So, in fact, why don't I go ahead and show it to you right now since we talked about it last class. And I'm not encouraging you to use this because this guy kind of falls into that same category as the, I++ putting it inside of like a println, where you kind of have to wonder whether or not you have to wonder whether or not the value you're looking at is the original value or the one larger value, when if you just put it on a separate line, it would be clearer to you. So there's something that's left over from the old days of C called an inline if statement. All right, so let me just dump this real quick. And let me show you, I'm going to just write a quick for loop for int I is equal to 0, I is less than 10, I plus plus. Now what I'm going to do is I'm going to use an inline if statement to either print out that I is even or odd. Okay, so what I'm going to do is we're going to ask the question. Actually, yeah, I think it'll work in this context. So we're going to say I mod 2 equal to 0, question mark, system.out.println even, colon, system.out.println odd. Minimize this so more stuff shows up, and I'll minimize this so more stuff shows up. This guy does exist. It's equal to 0. Okay, I think we might need to write it this way to get the inline to work. All right, so something like this. So I'm going to print out something. All right. Now, what I'm printing out is going to depend on what the current value of I is. So embedded inside of this println, I'm going to come up with either the string even or the string odd. And I'm going to come up with that based on this Boolean expression. So each time through, I'm going to ask the question, if I mod 2 is equal to 0, that is the current value of I evenly divisible by 2? If it is, this is the true statement, even. So this guy right here will boil down to the string even, which is then the value passed into this println. The else is the odd here. So when I run this, it should alternate between even and odd. Does that make sense? First of all, this should look a little weird. You never have to use something like this. Every now and then, it might give you a little shortcut, because what's the alternative to this? I could say, if I mod 2 is equal to 0, then system.out.println even, else system.out.println odd. So all of that is equivalent to just this. But isn't this easier to read? Yeah. So this is a historical leftover, and it does have a purpose. So kind of along the lines you asked, this guy really isn't something that's abusable. You know, like the whole thing, inviting somebody to a party, handing them the house instead of handing them the address to the house. This is more of a, let's call it, I guess I usually refer to things like this as syntactic sugar. Okay, this is a compressed form of something you could write otherwise, but in quick little offs like this, because sometimes you will want a value to boil down to one or two things, one or the other thing, depending on a variable, depending on a Boolean expression. And in that case, maybe something this might make sense if you felt comfortable with it. But it's never going to be required. You could always just write it as the larger if statement and move on with life. Make some sense? So I will never quiz or test you over inline if statements. This is more just a trivia thing. Know they exist. Okay? Yeah, you could. But you wouldn't ever need to, right? You could still write the if statement and have two separate returns and know that only one of them got called. Yeah, so I can't think of a situation where if you didn't have an inline if statement, you couldn't survive. You can always just write the if statement and feel comfortable and not be confused by some like weird syntax. Because this is a weird syntax, isn't it? Or at least feels weird to us because it's something that's left over from a long time ago. Like we can kind of roll with this whole, this guy's still a Boolean expression, I get it. And now we just have curly braces instead of the colon and then the indentation stuff. We can roll with that. That's not a major shift. Start throwing question marks and colons in there. Now it's like, oh, what is this? It's like almost a memorization type thing. Okay, so let's go back to, oh, perfect. I might as well just rewrite it. Be good for the soul. So for int I equals 1, I is less than or equal to 1,000, I plus plus. I did give you the, I'll warn you again, I did give you the warning last time that if you're going to look up things on Google, don't copy and paste it, type it yourself. That's an important thing. So you'll get better at typing these things and making less mistakes. All right, so we'll ask the initial question. If I mod 3 is equivalent to 0, logical and, so double ampersand, no spaces, I mod 5 is equivalent to 0. And the thing I was pointing out before is a common beginner mistake is this. And he pointed out that, well, these are two separate things. So the logical AND operator requires that both sides be Boolean expressions. Okay, the left side must be a Boolean expression, the right side must be a Boolean expression. What's a Boolean expression? Yeah, any expression that boils down to a single value of true or false. Is this guy a Boolean expression? Yeah, we're going to take the current value of I, we're going to divide it by 3, we're going to look at the remainder, and we're going to see if it's equivalent to 0. The answer is either going to be true or false. Is this guy a Boolean expression? That guy doesn't make sense. I'm saying mod 5 equals 0. Well, the mod operator requires something to be on the left and the right. The left-hand side must be a number. The right-hand side must be a number to support division, right? So that we can get the remainder. And they actually need to be integers, right? Because remainders only make sense in integer division, correct? If I take 3.14 divided by 7, I don't get remainders. I get decimal point stuff, okay? So for the mod operator, the percent symbol, both sides need to be ints, integers. So this side here doesn't meet the requirements of being a Boolean expression. So it's not that it's a weird syntax that you can't do this, it's that this doesn't make sense when you boil it down. Now we have a Boolean expression on the other side. Go ahead.
I don't know why, but something is telling me that mod makes sense as an operator that exists.
Yeah, it would be a bitwise modulus.
Okay.
Yeah, so similar to what we did before with the AND. So it would take the first number divided by the second number and look at the remainder. Just to cover my butt, I'm going to say 99% certain of that. That would make sense to me. I don't know if I've ever used that operator, but just based on how languages are typically put together, that would make, that's the pattern. Put two operators together, and so that would be 0 mod 1 should give you a 1. 1 mod 1 should give you a 0. 1 mod 0 should give you an error, because now you're dividing by 0. Should give you divide by 0 error. So let's not go down that rabbit hole too far, but that would be my prediction of what the output would be. All right, so if I is evenly divisible by both 3 and 5, we're going to print out Fizzbuzz. Now, if I'm in this else here, now I'm going to write it kind of the bad way, and then I'm going to untell you something I told you last time, or I'm going to give you an exception to something I told you last time. So I'm going to say else. If I'm in this else, that means that at the very least I know that I isn't divisible by both 3 and 5. But could I still be divisible by one of them? Okay, so now I'm going to ask another question. If I mod 3 is equal to 0, then I'll do system.out.println fizz. I don't remember if they're capitalized or not, but whatever. Else, if I'm in this else, I know that they're not both evenly divisible by 3 and 5. Or that I know that the current number is not evenly divisible by both 3 and 5. I know that the current number is not evenly divisible by 3, but could it still be evenly divisible by 5? Yep, so I'll ask that question. If I mod 5 is equal to 0, system.out.println buzz. Now, if I'm in this else, I know that I is not evenly divisible by 3 and 5. I know that I is not evenly divisible by 3. And I know that I is not evenly divisible by 5. Therefore, it might be evenly divisible by other things, but we don't care about that for the Fizzbuzz logic. So we're just going to print out the current value of I. Like that. Okay. So this should give us Fizzbuzz Logic for the values 1 through 1,000. Now, what don't you like about this up here? What's troublesome about this if structure? Yeah, you got all these things nested inside of each other. Now, I'm telling you it's correct. We just saw it worked, right? But we probably would prefer a little cleaner, because really we're asking independent questions, aren't we? So now I'm going to situationally allow you to, well, I'm going to say allow, tell you that it's appropriate to break a rule we talked about last time, or 2 times ago, whatever it was. When I said that it's never wrong to use the opening and closing curly braces, even though it's not required. Okay? Now, technically, under an if, it's a statement. Under an else, it's a statement. Our common statement is the block statement, which is the open, closing curly brace that holds a collection of 0 or more statements. Now, what I would typically do is I would write that else if on one line like that. Now, if you're going to do that, you have to remember to go ahead and dump that closing curly brace from that else if, from the original else rather. Then I would write this else if as one line. Then I'd write this else. It's the catch-all. And we're going to delete that guy. That's the same logic. Because what we've done here is when we say else if, here's the else, and the body of that else is the if statement. Does that make sense? It's a single statement. So this would be a special case, if you will, where it likely makes more sense not to use the curly braces after the else if what you're doing is you're nesting an if statement inside of it. We're probably better off asking it like this. If they're both true, do this. Else if one of them is true, do this. Else if the other one is true, do this. Otherwise, do this. Same exact logic, but it looks a little cleaner this way. Probably looks a lot cleaner this way. Yeah.
Yeah, question. Actually, I don't know why, but if you put the if with the and operator behind the other one, and it'll give you a different output where the fizz.
So you're saying if I do else if on this one,
Yeah.
and then I throw this if before it,
Yeah.
okay? I'm going to have you answer your own question. Why is that different logic? It does give you different output. It gives you different output because it's different logic. Let's say, what's our first number that's evenly divisible by 3 and 5? 15? Okay. So when I pass a 15 in and I check it right here, what's going to happen? I'm going to get fizz because 15 is evenly divisible by 3. And if this happens, None of these happen. They're independent. They're mutually exclusive from each other. Okay? So, in this case, I mentioned this a few minutes ago, we're going to use our most exclusive Boolean expression first. Here's the thing that's least likely going to match up to. Okay? Because once I get past that, then I can check the individual 3 or 5. But if I'm going to check the 3 first, my logic breaks down because I'm never going to be afforded the opportunity to check if it was also divisible by 5. Make sense? All right, so this should give us our official output. And we'll say that that's perfect. We've looked at all 1,000 outputs, and it's great. Okay, so now what would be nice here is to take, well, first of all, any questions about this? Any more questions? Makes some pretty decent sense. All right, so now what would be nice is, I don't know if it's all that useful in the big scheme of things, but let's say we want to apply Fizzbuzz to all the numbers between 1 and 1,000, or possibly 1 and 10,000, or possibly 1 and 10, so on and so forth. We wanted to have some sort of limit on this. Now, for us, we can say, well, if you want to do it between 1 and 10,000, you just change the 1,000 to 10,000 and run it again, and there's your answer for that one. Or if you want to do it 1 to 10, just change that to 10, run it again, and there's your answer for that. Now, what if you wanted to do 1 through 10, and then you wanted to do 1 through 1,000? You'd have to duplicate this code a second time, so now it starts becoming a hassle. So what we might do then is we might take all this code and we might wrap it inside of a function, or in object-oriented languages, they're usually called methods. All right, so for right now, all of our functions are going to be static. So just don't worry about that for right now. Now, if I have a function, and this guy's going to take in an upper limit, so it'll take in either 1,000 or 10 or 100 or 10,000, whatever I want my upper limit to be, and it's going to do the Fizzbuzz logic. What kind of value should that function return? Is it returning a string? What does Fizzbuzz actually do? Doesn't just print out a whole bunch of crap? Does it actually produce a result afterwards? Or does it just display a bunch of stuff on the screen? It's not doing any math. Remember last time we looked at addnums here? Where we give it a couple of numbers, it adds them together and spits the result back out. With Fizzbuzz, we're not spitting a result back out to whoever called it. We're spitting a result out to the screen, right? We're printing stuff to the screen. So this guy is not going to actually return anything. But all functions have to have a return type because this is a strongly typed language. So we're going to say void. This guy will not return a value. It's going to do something. Well, presumably it's going to do something. Otherwise, we're likely wasting our time writing it. But it's going to do something, but it's not going to actually spit an answer back out. And let's call this guy Fizzbuzz. Now, typical naming conventions for functions is you kind of name them, you know, and kind of what they do, but usually you start off with a lowercase letter and then you put uppercase letters in the, you know, as you go along for reading it. Not required, just more naming convention. So you can call this guy Fizzbuzz with a capital F if you want, but this would probably be a common naming convention. All right, and we're going to take in an int upper limit as a parameter here. And I'll go ahead and paste all my logic in here. And the one thing I'm going to change is instead of putting 10 there, we're going to say upper limit. So now I have my identical Fizzbuzz logic. But instead of hard coding a number in here, when I call this function, I'm going to be able to tell it how far I want it to go. All right. So if I run the program right now, what's the output going to be? Nothing. Why? Never called the function. So this function down here, when we write a function, it's a chunk of code that we write once and potentially call, 0 or more times. In this case, I have the ability to do Fizzbuzz if I gave it an upper limit. But I'm never actually calling it, because remember I made the statement several classes ago that all programs begin and end with main? So when I hit play up here and this Java program runs, it's going to start at line 1 of main here and says, what would you want me to do? What do you want me to do? In this case, my main shows nothing. Make sense? So this program currently does nothing, even though it has a whole bunch of potential. So I'm going to go ahead and I'm going to call my Fizzbuzz function, and I'll pass it 1,000. And now it performs Fizzbuzz. I can then call that guy again and pass it a 10. And I promise you it did Fizzbuzz to 10. Well, you can see it here at the end. So there's the 1 to 10, and then here's the 1 to 1,000 before that. So it performed the entire Fizzbuzz logic 2 different times based on 2 different inputs. Now, you might want an upper and lower limit. So instead of defaulting at 1, maybe you say int lower limit, and maybe we pass in 1 to 1,000 here, and maybe we pass in 5 to 10 here. And now instead of I starting at 1 by default, we start at lower limit. Almost the same output we had before, except this is going to be 6, which is even divisible by 3. This is going to be 5, which is even divisible by 5. So this is actually the output of that second half. What would the output of this guy be? So it's going to be an infinite loop.
Would it not print
You don't think it's going to print anything? Why not?
anything? Because it can't do the
Okay, so for loop comes in this example, what's lower limit? 50. What's upper limit? 10. So this is what happens first. I starts off at 50. Then we ask the question, is 50 less than or equal to 10? It's not. It's false. Remember we talked about for loops are pre-check loops? So we ask the question before we execute the body of the loop. This is not an error, and it does do the for loop. It goes into the for loop, just the for loop fails the very first time. So, no, 50 is not less than or equal to 10. Okay, jump all the way here to the bottom. We're done with that for loop. What happens next? Nothing. Function's over. Make sense? So this guy will print nothing. All right, so now let's talk about strings. I like to refer to Java as a string-based language. And what I really mean by that is, in Java, if we can have something in the format of a string, we can do a lot of stuff with it. Strings are very malleable in Java. Okay, so now what is a string? A string is and we've worked with these before, it's a double quote followed by a bunch of characters. So we're going to say followed by a double quote. That's a string. Now this is a strongly typed language. So if we are trying to determine the type of something, what type is that? It's an int. Okay. What type is this guy? Char. How do you know? You noticed the single quotes. How did you know this guy was an int? We recognize numbers, right? So as people, we're like, that's 5. It's an int. How does Java know that's an int? Hmm.
Doesn't.
You don't have to declare it. 5 already exists. Does Java know about the number 5? Or did we have to teach it about the number 5? So right there, 5, Java knows about that guy. And it's going to determine that that guy's an int. But how?
Because we already defined it first.
But we didn't define it. I didn't define it anywhere. I didn't say something. I think what you're wanting me to do is say something like int I is equal to 5. Right? I didn't do that here. I just threw out the value 5. I just said 5. Java's fine with that. Java knows about 5s. And I promise you Java's going to determine that that's an int. So my question is how did Java determine that that's an int?
Double. Low.
No quote.
It'll determine that that one's a double.
Yeah. But
So how did Java decide that this one's an int and that this one's a double? These guys here are what are called literals. So this is the integer literal. So what Java has is they have and this goes for all programming languages, or let's say most programming languages. I can't think of one off the top of my head that wouldn't work this way. They have this thing called a literal table. Okay, or it could be called a literal table. It's effectively a list of all the, let's call it reserved words in Java. All the things that are, so for instance, in that list is going to be like if, because that's a reserved word. It'll be else will be in there as well. For will be there as well as all of our digits, 0 through 9. Make sense? So it's going to go and look up on there and say, does this guy right here, this is a single length element, does this guy match something in our literal table? It does. It's going to match the single value 5. If I had 2 5s, or 52, let's say, it'll match both of them, and since they're together, it's going to treat the whole thing as an int. But if we're just looking at the 5, it's going to look up in there and say, this guy is one of my literal values. What kind of literal is it? It's an int. That's an int literal. Now, Java didn't invent this. Numbers existed before Java, right? So all Java said is, hey, you might want to use numbers, so I know about numbers. And that has to be included in the language somehow. And that's through literals. So Java's going to look that guy up and say, that's a int literal. This is a double literal. This guy's going to be a char literal. And we identified it initially more simply by looking at the single quotes around it. Because how many different values can go inside those single quotes? We can only have one character in there, but how many unique values could we put in there? We could put an A, we could put a B, we could put a C. How many total different values could we put in there?
535.
Well, you're right, but you're slightly wrong. 65,536. Because it's 0 to, but that's good. I won't ever ask you that like on a quiz or something. This is more trivia knowledge. So it's an unsigned number. It's an unsigned 16-bit number. So it's 0 to 2 to the, it's 2 to the 16th power minus 1. 0 to that. All right, that'll give us 65,535. And then 0 is the smallest, which is 65,536 total unique values. And that's called the Unicode character set, which is a superset of the ASCII character set. Okay, so there are 65,536 possible things we might have in there, but every single one of them will be surrounded by single quotes if we're dealing with a char type. What type is this guy? String. How do we know? So use the double quote crap, right? Now, length of strings are a little bit tougher because now we have each one of these is going to be a character, so each element will be a Unicode character. But we have, from our perspective, an infinite number of Unicode characters we can represent. Realistically, it's probably either represented as a 32 or a 64-bit value in terms of the number of elements. So this can hold, let's call it between 2 billion and what is it, 4 quintillion individual values. There isn't a great reason why it couldn't even be implemented as arbitrarily large at the cost of performance, but we don't need to worry about that. Just it holds a whole bunch of chars. And we identify this guy as a string because we see the double quotes. What about this dude? That's a variable. How do you know?
Because it doesn't look like an int, and it doesn't have any quote.
Okay, so process of elimination, right? So process of elimination is he's not an int, he's not a double, he's not a char, he's not a string. So he's either a variable or what's the other option? How do we know? What would this guy be? That guy is a function because we see the opening closing parentheses on it. Or he's the same answer as the or for the B. Or it's an error. Right? These are guys, this guy we presume must be a variable. So what do when we see a variable, our job is to get the value out of that variable, right? Because I can't work with B. I need to find the value that lives within B. And that's called resolving a variable. And where do variables live? They ultimately live in memory, but we've given a name to it in the middle. Already mentioned it today. They live in scopes, right? So we have various scopes in our program, and they're effectively a collection of variable name value pairs, right? We have a name, and we have a value. So B, if we find it inside the scope, it's going to have the name B, and it's going to have some value associated with it. And in a strongly typed language like Java, it's also going to have a type that'll tell us that B is an integer, or B is a char, or B is a Boolean, whatever it is. Okay? We know this guy is either a function or an error because we see the opening and closing parentheses. All functions have parameter lists, even if they take no parameters. We happen to have a function here that takes 2 parameters. We have another function here that takes 2 parameters, but I can write a function called static void do nothing that takes no parameters and does nothing. Okay, and that is a legal function. It's a function that returns no values, doesn't return anything. It's called do nothing, takes 0 inputs, and in fact, true to name, does nothing. But it's still a function because I see the opening and closing parentheses on it. That's how I can determine that this guy's a function and not a variable name. And I'm going to say ish after that, and I'm going to explain why here in a second. If we've determined this guy is a function, do functions live in scopes as well? Well, this do nothing thing, he lives inside of this opening and closing curly brace from driver, right? And we've kind of advertised as these opening and closing curly braces as being representative of a scope. All right, it's not 100% truth, but let's call it close to a truth. So at the end of the day, what is a class? A class is a collection, and we mentioned this last time, I think. A class is a collection of fields, variable names, functions or methods, and then also constructors, which we've talked about it previously. We're going to see it in Java probably next class. So we have a collection of functions in here. Where is this guy accessible? Where is this guy accessible? Where can I call Fizzbuzz? Where do you suspect I'm allowed to call Fizzbuzz? Anywhere inside the class. Now, an important caveat there. So let me throw this out here. where am I allowed to call A? Yeah, so the previous question was, where can I call Fizzbuzz? And the answer to that is anywhere in the class, because Fizzbuzz is a method that's defined within the scope belonging to the class. Now, A is a variable that's defined within the scope belonging to main, right? But it would be incorrect to say that we could use A anywhere in main. This is not allowed. I can't use A before I've defined it. So even though these guys are very similar to each other, they're not identical, right? Now, it does make sense that variables, we can't use a variable until after we've defined a variable. So that side of things kind of makes sense for us, right? Now, why then can I use Fizzbuzz anywhere? Because we've seen it. We're using Fizzbuzz right here, and we have not defined it yet, right? It's defined down here. But this works.
Our program, our Java program start and end with main. So everything in the main is calling for the function that we in that.
Okay, so that's not a bad suggestion. But so addnums is defined down here. So I'm just going to change something in Fizzbuzz. I'm going to say addnums 2, 3. That's allowed as well. And I'm not even involving main there. So I'm using a function that's not defined yet inside of a function that's not main. So this indicates that functions defined in this scope are available anywhere in this scope, even before you actually define them. Now that's not always been the case. In some in early C compilers, we had this idea. Let's call those compilers. Now, what's a compiler again? What does that guy do?
High language.
Yeah, it converts a high-level language to a low-level language. So in our case, it converts Java into Java bytecode. So we used to have something called a single-pass compiler. And what a single-pass compiler does, so before we can actually, during that conversion process, what we would do is we would start going through main here, and in a single pass, we'd get to this thing called Fizzbuzz, where we say, never heard of it, error. So then what would we have done? We would have put main actually at the very end of our class, so that all the other things were hit before we got to main. But then sometimes you run into these chicken or the egg problems, where you had one function that wanted to call another function that was a function before it, or a function after it. And now the function that wanted to call something that wasn't defined until after it couldn't be called. Make sense? That's a problem with single pass compilers. Now, in earlier languages, so we had a couple of C programmers in here, what was our workaround for a single pass compiler? Anybody know what the early hack was to, because that's something that would be common, right? I might want to call addnums from within Fizzbuzz. That's not an unreasonable request. But I'm telling you, in early programming languages, in early Java or early C compilers, this would not have been allowed as I have it written. But would you agree that that constrains us as programmers? That's really something that needs to be able to work. Correct? So what we used to do is something called prototyping. Did you ever, when you did C, did you ever do anything with prototypes?
Yeah.
So why didn't you answer the question?
Sorry.
Because you're paying attention to something else, right?
Sorry.
All right, so what we would do is up top here, we would have something like static int add nums int, something like that. You wouldn't even have to say the name of the variable because you're just saying here's a function called add nums that returns an int that takes 2 integers as parameters. And what this would do is, because this is kind of like hinting at, this is prototyping that function that will be late. We're promising we'll define it later. Okay, so that when we get to, and same, we'd have the same thing here for Fizzbuzz. So when let's just put add nums in here, add nums 2, 3. So when we get to this line and we're trying to compile it, we don't have to guess. We already have loaded into our symbol table the fact that there is a function named add nums that takes 2 integers and returns an int. Therefore, I can validate that this guy follows the rules. That make sense? So that's how we accomplish that. So in the early days of C programming, we had a bunch of prototype functions at the top of our program. Now, to alleviate this problem. Now, having said that, for a large program, how many functions might you have written in a large program? If we round down, is the answer a lot? All right, so you might have this gigantic list of prototype things at the top here before you even get to code. So what was our fix for that? So early fixes was prototyping. Then what did you say?
You put the prototypes or maybe even all the function definitions in a separate file and just include that.
Yeah, so we had something called header files. So sometimes what you would see at the top of a C program, and you've actually, when we wrote one before, you saw it. We had like include, maybe we would call it driver.h. And actually, usually it would be single quotes around it because it was a local thing. So inside of driver.h was our prototypes. So it might just be a big list of function names like this. And having include driver.h here and having a big list of things here functionally is no different. It's visibly different to us as the programmers. We don't have 300 functions prototyped at the top. Instead, we can actually put our prototypes inside of different header files if we wanted to, and we would just include them at the top here. And one nice thing about a header file that really, header files are typically not used today in our modern languages because we have multipass compilers, but there's still some benefits to a header file that we're losing out on today. You know, we kind of get, we get it back a little bit now that we have the ability in some of these IDEs to, I think, is there a way I think I can right click and can I collapse all? I think there's a way to collapse all. Yeah, I don't see it anywhere in there. I'd be very surprised if there's not a way to do it somewhere in there, but we'll just manually do it. So we can come in here and we can minimize our functions. Doesn't this kind of look like what I'm advertising a header file looks like? Just a whole bunch of method prototypes. So at a glance here, we can kind of see the various abilities that our program has within it. Make sense? Okay. So, whereas with header files, there is an advantage sometimes where you can kind of go and look at it. It's almost like instructions in how you could use this. This all went away when we got to multipass compilers. So what would happen is the compiler would go through initially and pick up all your symbols, pick up all your functions in terms of names and what they took. Effectively self-prototyping, saving you from having to actually write those prototypes at the top. Then on its second pass, it would validate. That makes some sense? So we automated something that previously wasn't automated, but it wasn't that big of a deal beforehand. But we do see that if we were limited to not being able to call a function until after it was written, that does put some constraints on us from problem solving. Because now you can't have functions that necessarily rely on each other because they weren't defined yet. So it becomes I think an interesting thing. Okay. So we want to write a function called makeChange that takes a double as a parameter and displays to the screen the correct, well, we actually want to take a double as a parameter for cost and a double for payment. And displays to the screen the correct breakdown of the most efficient change that can be given in terms of dollars, quarters, dimes, nickels, and pennies. So you don't have to deal with values larger than $1. Okay? So, for example, if somebody passed in the cost was $3.75 and the payment was $5, the change should print out $1, 1 quarter. Make sense? I give them $5 to buy something that's $3.75. How much money should I have coming back to me? $1.25. So my change is $1 and 1 quarter, $1.25. Training the McDonald's employees. That makes sense? So, am I actually going to be returning anything here? Or is this just displaying stuff? Just displaying stuff, right? My two parameters are going to be double cost and double payment. So your assignment for Tuesday is to implement this function. Questions, comments, concerns, bribes? All right, I will see everybody on Tuesday. Don't forget to let me know about the hackathon as soon as possible if you want to be included so I can start forming teams and make sure we have arrangements. Also, tonight is the first Grace meeting, 5 p.m. in this room. I strongly encourage you to come. That's our women's chapter of ACM computation thing. We're going to have a traditional one as well, but it's not just for women. It's for everybody. Okay? So, strongly encourage you to come. I will be here, 5 o'clock tonight.